Today, we will face three approximation methods of the area below a parabolic segment. Archimedes invented the method to calculate the area under the curve. The method consists in inscribing rectangles with equal bases within the parabola segment, in order to best approximate the area below the parabol. Archimedes' method is called method of exhaustion. The total area of polygons, in this case rectangles, converges towards the area of the approximated function. By iterating the exhaustion method, the bases of the rectangles are progressively reduced, while the number of the rectangles increases. The area of the curve and the integral are finite, therefore, the total area of the rectangles must be finite too. N times h, where n is the number of rectangles and h is the length of each rectangle's base, is a quantity that must remain the same. Archimedes' method is a part of Riemann-Sum's method. This is an approximation of an integral through a finite sum of terms. An application can be the computational of areas below the curve, which is an integral over a single variable. In this case, Archimedes' case, the term of the sum are the areas of the rectangles. The Riemann sums can approximate a function with other polygons, more suitable than rectangles. An example of this are trapezoids. This is the basis of the rule known as trapezoidal rule. By relaxing the condition of having all the polygons' bases of the same length, the Riemann sum, using rectangles, can be extended to get the Vegas algorithm. The trapezoidal rule is a method that uses a trapezoid instead of rectangles, all with the same base. The trapezoidal area calculation can be intuitively understood as the area of the rectangle, with the upper base passing through the midpoint of the upper base of the trapezium. This provides a better approximation of the overall height of the function within the range between x and x plus h being the base of the trapezoid. This method is more effective and precise than Archimedes' one, as the trapezoid has the upper base inclined following the function, and therefore approximates better than the rectangle with the horizontal base, the area below the curve. This method finds its roots in Peter's Lapage's scientific article, published in 1978 on the Computational Physics Journal. The non-constant size of the bases in the Vegas method is caused by the iteration mechanism of the algorithm that implements it. The regions where the function has higher values are sampled more. This is motivated by their greater relevance to the value of the integral. More accuracy is therefore more effective in those areas to decrease the overall error on the integral. At each iteration of the Vegas algorithm, an m number of points is added to evaluate the function. These are distributed in the integral's domain in proportion to the value of the function in each interval. The average value of the function in each interval is calculated by the average of f of xi, with I being from 1 to n, when n are the evaluation points of the function in each interval. The efficiency of these methods can be quantified by the number of function evaluation needed to achieve incremental levels of accuracy. This metric is often effective in evaluating the computational power needed to implement the different methods. As we can see from the graph, the Vegas method, which is represented by the blue line, is both the most effective and the most accurate among the three methods. We can notice that the trapezoidal rule follows this both in effectiveness and precision. It is represented by the orange line. Last but not least, we find Archimedes' method, that is the worst one, both in effectiveness and precision.